In this last video cast of Chapter 19, we're going to take a look at how the relationship between delta G, free energy, is related to the equilibrium constant K. And we'll see how those two things can be calculated and compared or actually related to one another. The equation that we'll be looking specifically at to start with is how delta G is equal to standard condition delta G plus RT natural log of Q. And remember, Q is called the reaction quotient, which means that's what the ratio is of products divided by reactants to the power of its coefficients at non-standard conditions. We're starting on page 16 of your sample problems, and we're going to finish this section of 19.7 on this page and the one following. The first question says, using the production of ammonia equation, calculate delta G at 298, which is standard temperature, for a reaction that consists of 1 atmosphere of nitrogen, 3 of hydrogen, and 0.5 for ammonia. Now, we did something like this back in chapter 15 when we studied Le Chatelier's principle. And if it was at standard conditions, all of these things would be at 1 atmosphere of pressure. But now we're at non-standard conditions where this is 1 atmosphere, this is increased to 3 atmospheres, and this is decreased to 0.5 atmospheres. And we just qualitatively took a look at this equation according to Le Chatelier's principle. If I increase the pressure of this substance and decrease the pressure of this substance, we'd think that we should shove the reaction to the right, and therefore increase the driving force of the reaction, and therefore the free energy should become more negative, meaning the reaction is more spontaneous. Well, let's see if that really happens. If you recall, last video cast, we did a calculation back on page 15. I'll just put this one up here as reference, where we calculated the standard free energy change at standard conditions, 25 degrees Celsius, for this same process. And we ended up with negative 33.3 kilojoules for that standard process of the production of ammonia process. This is on the page before, page 15. Now we're on page 16, and we'll use that result to help us find the delta G at non-standard conditions as well. So here's the equation that we're going to use, and we're going to calculate delta G at this non-standard condition. But before we can do that, we've got to find Q. And remember, Q is going to be equal to the products, so the pressure of NH3 to the second power, divided by the reactants, N2's pressure to the first power, I should put a P there for pressure, and the pressure of H2 to the third power. Notice the power of the coefficient right here, If we put these values in, for NH3, we have 0.5 atmospheres. That'll be squared. To the nitrogen, that's at 1 atmosphere to the first power, and hydrogen, which is at 3 atmosphere, and that will be cubed. When you calculate Q, you end up with a value of 9.3 times 10 to the negative third. Now we can put that into this equation to find delta G at a non-standard conditions. Delta G is equal to delta G at standard conditions. Remember, that's what the little circle here means. And we said we looked back at the last video cast's results, and it was equal to negative 33.3, and that was in kilojoules. Be careful of the units now. Notice this is in kilojoules. Plus R, and the R that we use here for the universal gas constant is 8.31, and notice the units, joules per mole times Kelvin. Notice this is in joules, and this one's in kilojoules. So we'll convert this one to kilojoules as well. We'll just put a relationship that there's 1,000 joules in 1 kilojoule, and now we've converted the universal gas constant, so it's in the same kind of units as our delta G before. We'll multiply that times temperature. Temperature is 298 Kelvin. Notice our kelvins will cancel with our kelvins, and now our joules go with our joules, and so we're in kilojoules per mole. And then we multiply that times the natural log of Q. So I put ln, and Q is 9.3 times 10 to the negative third. So if I zoom out just a little bit, you'll be able to see the entire equation. if I put this into my calculator, calculate this part first, and then add it to the negative 33.3, we find out that we end up with negative 44.9 kilojoules per mole. Look what happened to our number. Normally we started at negative 33.3 and it became more negative. Remember, more negative for delta G means more driving force or more free energy for the reaction. And that's what we predicted using Le Chatelier's principle, that if you increase the concentration on this side of the reaction, it should shove the reaction more to the right. And so at non-standard conditions, you can always use Q, temperature, gas law constant, and the regular standard condition, delta G, to find out what would happen to the free energy at those conditions. Flipping over to our last two sample problems in this chapter, this is page 17 now, we're asked to use standard free energies of formation to calculate the equilibrium constant now at 25 degrees Celsius for the reaction involved in the production of ammonia equation again. The standard free energy for this reaction we just used in the last problem. It was negative 33.3 kilojoules per mole, or there it is in just joules per mole as well. So now we're going to use an equation to actually solve for the equilibrium constant. And if you remember, the equilibrium constant, or equilibrium for a reaction, occurs when delta G is equal to 0. So if we use our last equation, delta G is equal to delta G at standard conditions plus RT natural log Q, if we're at equilibrium, delta G is equal to 0. So now we have delta G is equal to delta G at standard conditions plus RT natural log Q. And if you solve this, it turns out delta G at standard conditions is equal to negative RT natural log Q. This is the equation we're going to use in here. Except we have to change one thing. Now we no longer have Q, because we've said we're at equilibrium because delta G is equal to 0. So we don't put the letter Q in here anymore. We change it to natural log of K. And so now our equation becomes standard free energy at standard conditions equals negative RT natural log K. And we're going to want to solve for this K. Well, we know that the standard free energy change for this reaction was negative 33,300 joules per mole. We'll use the joules per mole because we know R is 8.31 joules per mole times Kelvin, and we'll keep the units the same in joules and joules. Temperature is our standard temperature, which is 298 Kelvin. And then we have natural log of K, and we're going to solve for this natural log of K. So dividing both sides of the reaction by negative 8.31 and 298, divide both sides by negative 8.31 and 298, we end up with the natural log of K equaling 13.4. Now, if you want to solve for K, you don't divide both sides by ln. It doesn't work that way. We have to use a special key on your calculator. That's the e to the x key. So when you put e to the x and then you type in 13.4, you find out that K is equal to approximately 7 times 10 to the 5th. 7 times 10 to the 5th. Does that make sense? Well, it can tell us the direction and extent of the reaction, but it tells us nothing about the rate at which the reaction will occur. And so this large equilibrium constant indicates that the product is greatly favored. We will definitely produce a lot of this ammonia. It's favored, but it doesn't tell us how fast the reaction is going to happen. It means we will produce a lot of products, though. So last question, last sample calculation. Use data from Appendix C to calculate the standard free energy change, delta G, and the equilibrium constant K at 298 Kelvin for the reaction, and we have a new reaction there of hydrogen and bromine making some hydrogen bromide. Well, data from Appendix C would allow us to find delta G at standard conditions, and to do that we'd take the summation of the products and subtract from that the summation of the reactants, just like we've done before. And just to speed things up a little bit, if you look these up, you'll find HBr, and you look these up, you'll find H2 and Br2, and it turns out to be negative 106.4 kilojoules per mole. And it turns out that hydrogen and bromine are in their standard conditions, and so they're going to have delta G's of 0. And so in effect, the delta G here for the reaction is just simply the sum of the products times 2, because you notice there's a 2 right here in front of the HBr. Okay, then we can take our equation. Delta G is equal to, at standard conditions, negative RT natural log of K. And it's asking us to find the equilibrium constant. So we know that delta G is negative 106.4, and notice this is kilojoules per mole. We'll do it in kilojoules this time. And R is 8.31. So let's take and put that down, 8.31 joules per mole times Kelvin. But remember, this is kilojoules, so let's convert this side to kilojoules by putting joules down here. Kilojoules is our new set of units, and there's 1,000 joules in 1 kilojoule. The temperature is 298 Kelvin, and then our natural log of K is what we want to find. So solving this by dividing both sides by these numbers and dividing this side by those same things, we end up finding natural log of K is equal to, well, it turns out to be let's see, I don't have that offhand, but when you solve it, it's a pretty big number. And then when you solve for K, it turns out to be 5 times 10 to the 18th, if you want to check it out in your calculator. A really big number, which tells us HBr is very favored. Now you should also take a look at one of these problems in terms of solving for something else, because they might give you the equilibrium constant, and perhaps they'll give you the free energy, but maybe they won't tell you what temperature you're at. And they might tell you, just assume that the standard free energy change is the same even though we're not at standard conditions. And then you'll have to solve for that temperature. Well, that's possible. They could ask you for that. Or perhaps they'll tell you the equilibrium constant and the temperature, and they'll ask you what delta G is. Well, then you can plug these numbers in and you can solve for delta G.